15.6 Surface Integrals Part 1. What is the average temperature along the edge of a plate? This is the type of question we were able to answer using line integrals. Given the temperature function and the region of the plate, we did the following. We parameterized the edge of the plate using arc length. If we call the edge of the plate C, then we parameterized C using arc length. Then we wrote the temperature function T on the curve C in terms of the parameterization. Then we integrated the temperature function over the curve and then divided by the length of the curve. Later, we discovered that if the curve was not parameterized by arc length, but for example by t, we could still find the line integral using t. We want to be able to do the same type of task on a sphere. Suppose a sphere has a known temperature distribution. Perhaps it is cold near the poles and warm near the equator. How do you find the average temperature over the entire sphere? Analogous to what we did for the edge of the plate, we would like to add up the different temperature values over the sphere and divide by the area of the sphere. So the question will be, how do you integrate a function over a sphere? And this is the type of question we answer using surface integrals. Now this is just part 1 of surface integrals. In part 1, I'm going to focus on just the parameterization. Again, as a review, when we did the parameterization of a curve, we had a line in T mapped to a curve in the XYZ space. For a surface, we're going to map a rectangle to a surface using a parameterization in terms of U and V. For example, we could map a rectangle to the surface of a cylinder using this parameterization. If we use this parameterization, then the horizontal line v equals 1.6 is mapped to a circle of radius a in the plane z equals 1.6. The vertical line u equals pi is mapped to the vertical line negative a, 0, v, where v runs between 0 and h, so it gets mapped to a vertical line. Another parameterization is this one, which uses spherical coordinates. Using this parameterization, a horizontal line v equals pi over 2, so that line pi over 2 gets mapped to a half circle which is a line of longitude. And the vertical line u equals pi over 4 is mapped to a circle in a plane z equals a radical 2 over 2. Another example is the mapping of a rectangle to a cone. A horizontal line v equals 1.6 gets mapped to a circle, and a vertical line u equals pi gets mapped to a line that starts at the vertex of the cone and runs up the side of the cone. Now let's try to do a parameterization ourselves. Let's start off with something rather simple. How about a plane? Well, planes doesn't take really that much work. All we have to do is solve for z. Let u equal x, let v equals y, and whammo, we have our parameterization of a plane. So it's a mapping from uh, a, a rectangle to a plane in three-dimensional space. Let's do something more complex. How about a paraboloid? Z equals x squared plus y squared, where z runs from 0 to 9. Well, let's just borrow from polar coordinates. Let's have x be v cosine u, have y be v sine u. And so the parameterization where x equals v cosine u and y equals v sine u is a very good start. What would z be? So what is z in terms of u and v? And not only that, what are the bounds on v? Well, we know we want x squared plus y squared to equal z, but x squared plus y squared using parameterization equals v squared. So if x squared plus y squared equals z squared, that means that if x squared plus y squared equals z, and that means that z needs to be v squared. So just use that in our parameterization. And then it's not too much work to figure out what the bounds on v are. Z is running from 0 to 9. And so we want the upper bound of v to be 3, because 3 squared is 9. So the parameterization of the paraboloid has been found, and this is what it is. All right, so I take care, and I will see you in part 2.